The two main test parameters for the series of testing we did in Chill-Off 2 were we varied the chilled water temperature from 45 to 60 degrees Fahrenheit, and we also varied the server area inlet temperature from 60 to 90 degrees Fahrenheit. You can see sections there where one parameter was held constant while we varied the other so that we could determine what the contribution to the performance was while just varying one parameter. There were 7 different combinations. We divided the devices being tested into 3 categories. First category was rack coolers. There was 4 rack coolers that we tested, APC, 2 from Knur and 1 from Rittal. Next category is we call row coolers. There was a row cooler from APC that we tested in 2 different modes. One was a single backup mode, or forgot the word for it, and then also the mode where we had twice as many units running as needed. So there's 2 tests there, and then the other was a row cooler from Liebert. Third category is passive door coolers. There was 2 water door coolers and 2 refrigerant coolers from Liebert and Sun. Also in this category, probably the closest category for the clustered systems test would fall into this passive door cooler category because it doesn't contain fans. Okay, so in order to try and make everybody happy, which in retrospect may not have been the best thing to do, I came up with a number of different type of metrics, and also to add the correct amount of obfuscation or confusion. Anyhow, so I used 2 general metrics. One is SCOP, which comes from an ASHRAE 127 standard for testing unitary air conditioning systems. The other is COEE, which I made up. So
why not?
Actually, the concept is very close to PUE, but I didn't want to call it PUE because it does not contain some of the components that PUE has, for example, lighting, UPS systems, backup system support, and so forth. So I didn't want to call it PUE or partial PUE, which would actually be slightly closer because partial PUE people are working on the definition of that metric, and I didn't want to contaminate that process. So these are the 2 general metrics. Now, to make things even more interesting, for SCOP we have 3 different options. And the 3 options include more power components or less power components, A through C. For COEE, there's also 3 options. We have COEE, COEEC, and COEE-DT just for the clustered systems test. Now, this is going to get a little confusing on the next slide, so you're going to have to kind of bear with me. I'm going to explain these. So SCOP is defined in ASHRAE as cooling provided divided by the cooling power used. So SCOPA considers the power going to the CDU, if you have one, and the power going to the cooling device. Okay? SCOPB adds an additional item, which is the pumping power for the chilled water distribution, to that equation. And SCOPC, which is probably the best metric to use for testing just the cooling performance of a device, also includes the power needed to run the chilled water plant, which turns out to be probably the dominant, well, it's definitely the dominant power using component in the metric. Okay. Now, see the 3 versions of COEE. So this one follows the PUE definition, the total power needed plus the IT power divided by the IT power. So it's pretty straightforward. Again, I didn't call it PUE or partial PUE because I didn't want to contaminate their process. The COEE. Now, this was interesting. one of the reviewers of the process and one of the companies that had a device being tested pointed out that the SCOPC metric relates directly to the COEEC metric by this equation. I have a slide with the derivation, but the thing that it does is it compensates for tests where there was over or undercooling done by the device. So we had some cases, for example, this one example here, for whatever reasons, the testing setup, the device was overcooling, and so it gets charged with the power needed to do overcooling, but the device, the denominator is only the IT power. So it actually gets charged too much. So, but this metric resolves that problem in that it's when the IT power equals the thermal power. So that's what that metric does. Okay, that's credit to Vic Mahaney from IBM for noticing that and helping with the derivation. Okay, this definition is going to be worse. So in order to make the clustered systems people happy, I came up with a metric that compensates their results for the fact that they don't have fans inside the servers. Because as you know, the PUE type metric doesn't give you any credit for having lower server power. So this metric, the COEEDT, compensates for that, and it is the performance that a normal system would have in order to result in the total power used being equivalent. Okay?
Everybody get that?
I'm not sure if I got that, but it's a little bit tough to wrap your mind around, but that's what it is. Thanks, Dean.
You're welcome. Here to help.
Yeah. So anyhow, that's what we did. So what happens when you do this is you get essentially a PUE that's under 1. It's another large reason not to use PUE. I don't want to get up here and say that we had a PUE under 1. So I don't want to have to try and explain that. Anyhow, so those are the 6 metrics. Yeah.
What's the normalized server power normalized to?
Oh, God. So it's probably Phil can probably, yeah. Phil, you've been so helpful over the years. It's the power needed to supply the same amount of compute. So in the case where, for clustered systems, you have to put less power into the servers to get the same amount of compute to happen. Now, it turns out that we used the same servers in these different tests, so we were able to make the comparison directly.
Specifically, it's the fans and the servers and how much they consume over the load.
Right. When you take those out, this compensates for that because they should get credit for the same amount of power or the more compute delivered for the same amount of power.
So is the denominator with the fans or without the fans? Normalized server power is with?
And I'm sorry, you are? No.
Yeah. Yeah. It's been kind of a long day. It's my second presentation. So.
It was consistent, Mark.
Is it okay if I go over that afterwards with you? It's one or the other.
Keep on going. Keep on going.
Okay. Moving right along. Okay. So thanks to Mark Heidemann and Taylor Engineering, we put together 2 chilled water plant models to use to calculate the results, because if you don't know the power that's being used to making the chilled water, you don't have a very complete analysis. So we made, Mark put together two plant models. It follows the ASHRAE code minimum guidelines for the code minimum plant for California. The data that we used was Santa Clara, 24/7, the average for the whole year. The second model, the Plant B model, adds a waterside economizer to that. So that's the only difference. So we just wanted to see if, what are the cases where a waterside economizer would help you, and how much would that be? So, okay, now we get to the what we're calling the money slide. Here's the results. This is one way of displaying a million spreadsheet cells. There's a number of things we can tell by looking at this, or that might be show a trend. One trend is that the rear door coolers seem to be have a slight advantage. This particular graph has all the devices of one type averaged together, so this doesn't show individual devices. I don't want to get into why I did that. There's some companies that didn't want that to be shown like that, so we didn't show it like that. Anyhow, on the average, the passive rear door coolers look to have a slight advantage, maybe 4 or 5% overall. Another thing to look at is that and that's the green line there. If you can see, it says rear door. Another thing to point out is that between plant model A and B, at the cold chilled water temperatures, there doesn't seem to be much of an advantage. At higher chilled water temperatures, maybe as you get towards 60 degrees Fahrenheit, you see a few percentage increase overall. So this is something to consider. For sure, you would want to review this with an engineering firm for your particular plant. But for the models that we have, this is the result that we got. Another interesting thing is that you can see the direct touch cooling is what we called it here, and this is the clustered systems device. It has a definite advantage compared to the other things we tested, and it's primarily due to the savings in power that were in the server fans, as far as we can tell. So that's why that's about a 12-13% improvement that they had in performance, and that's approximately the savings in their type of design. The blue line, you'll see it kick up on the rack cooler there at the end. That's because some of the devices tested either had controls improperly set, or their fan control systems couldn't handle high inlet air temperatures. We tested at 80 and 90 degrees. That's not common. It might be more common nowadays, but maybe a couple years ago it wasn't that common that you would have your data center running at 90 degrees Fahrenheit for a server air inlet. So in that case, some of the fans kicked up, and when those fans kicked up or went to full speed, they kind of shot themselves in the foot as far as energy efficiency. So the device power went up, and then you can see that the PUE, so to speak, went down. The lower number, I should have pointed out, lower numbers on this graph are better. So probably the most important thing in the graph.